Well, thank you, Jay. Great to be here. And before I start, I'd just like to acknowledge right up front some of the research teams and funders that are involved instead of at the end. The topic is, as Jay said, is I'm going to be talking about sustainable beef production, but from a technology point of view, I'd like to just acknowledge and go through some of the advances that have been made. I put this up here just to sort of get your attention and to show you the whole area of sustainability in beef production is really forefront in the food service industry and in the consumer's mind. And in this particular case, McDonald's has stated publicly in a release in January that in 2016 they will start sourcing sustainable beef production. Whatever that means, we're not sure. And that's interesting. And the reason I say that is, and the beauty of some of these large food service companies is they are aligning themselves with some pretty important individuals. In other words, McDonald's and Walmart are aligning themselves with what we call the Global Roundtable on Sustainable Beef Production. Many, many stakeholders are involved in here. And really what they are saying is that, at the general sense, they're establishing principles of what this means. And it really means that it is a balance between the resources that the world has in the air quality and water quality and the development of individuals and communities. Rural development has to be in there. It is also about looking at having food security, safe food, affordable food, and food that has good quality. That needs to be balanced with animal welfare issues, codes of practice, and of course, the health of animals, which is so important. The topic that I'm going to be covering a little bit in more detail is this whole area around progress. In order to be sustainable, you have to have progress, scientific progress in technologies, but also in terms of organizational management and how we look at the structure of these various systems. Well, I like to go to this really nice piece of work that was developed by that was researched by Judith Kapper in the U.S. It's about the sustainability of North American production systems over the past 30 years, and essentially science and technology has made some of these changes. So if I say the same amount of beef now requires 88% of the water, 81% of the feed, 70% of the animals, 67% of the land. And all of that results in about a 16 to 20% decrease in the carbon footprint of beef production. And what I'd like to say is that all of these changes have come about due to science and technology, advances in life science and technology in the area of nutritional management, health management, feed additives, the area of crossbreeding, and what I would call traditional breeding practices. Maybe I'll call that Breeding 101. So what's the problem? Seems like we're doing okay, so what's the problem? Well, the big problem is that we now have to do this faster, and we have to do this with more attention being paid to the social well-being, the environmental friendliness of a practice, and of course, it all needs to be economically sustainable. If it's not economically viable, then it's very unlikely that these types of things will go. Well, there's a couple solutions. There's more than a couple, but I'm going to dwell on just two of them. One is that we could continue on in what we're doing in terms of improving system production management, and it will make some pretty good improvements. Here's an example that I like to bring because it's a homegrown example. It's called swath grazing. A lot of work that we do at Lacombe Research Station is involved here, but essentially what it does is it takes advantage of our knowledge of the system. It says, you're a cow, go out and get your food. Right? Instead of us sort of collecting it off the field, spending energy to bring it into a feeding place, and then hauling the manure back onto the field. So it is a very sustainable type of a system. You can see the numbers at the bottom in terms of fuel savings, cost of feed savings, and the reduction in land use. The other technology, of course, is one that I really enjoy working in, and that's the area of genomic selection. And it's what I would call breeding 2.0. So let's just sort of, to put it into perspective, essentially what we're taking is old techniques that we've known for many, many years in traditional animal breeding and applying genomics to it. And really, in this particular technique, what we need is a really large reference population. And this is where funders like ALMA, Alberta Meat and Livestock Agency, and of course, Alberta Innovates Biosolutions comes into play. We develop this large reference population where we have animals that have really detailed phenotypes, characteristics, and really detailed genotypes. Let us say 50,000 bits of genetic information that we look at. And those bits of information, we're going to call them SNPs. So remember that. I'm going to tell you what that means, but I'm just going to say those basic units of inheritance are called SNPs, and we'll be looking at those very carefully. So what is really required here is that we then have to use this reference population to train our prediction equations. And we do this in this example. It's just a small example. You see that AT, that represents just one of those SNPs on a chromosomal pair. And you notice below we've got some various alleles. We've got AA, AT, and TT. And you'll see that as we change those alleles, it's related to different levels, in this case, of growth. So AA is associated with 0 grams increased growth per day, whereas TT is represented by 40. And essentially what we'll do is simultaneously fit all 50,000 SNPs into a prediction equation, and then use that prediction equation to create a score. You know, how well did you do at school, kind of a deal. And then we'll take hair samples or blood samples or any kind of tissue sample from what we'd call our selection candidates and use the molecular breeding values to decide on how we deal with them. Well, let's look at. Here is our population. I'm proud of this. This took probably over 5-6 years to create. Hate to say, but about $3 to $4 million. So these types of databases just do not get created. As you can see, we've got about 9,000 cattle with our favorite trait, which is called residual feed intake. And we've got the same 9,000 animals that have detailed genotype, 50,000 bits of genetic material. This scatter graph here, each dot represents an animal. So on there's over 9,000 animals, and you can see they vary quite nicely in terms of their summer efficient. So those animals that are below 0 are animals that eat less but produce the same amount. And those animals above the 0 line on the y-axis are those animals that eat more but produce the same amount. A colleague of mine, Erasmus Okine, he essentially said, those animals are eating for fun, right? They're really not doing anything with them. But I know I've gotten in trouble several times, Erasmus, for saying that, so that's just between you and I. So let's just take a look. From that large database, what can we do? Well, the very first thing we can do is we can create what we call traditional breeding values, estimated breeding values. Okay? And we could use those, and we can select animals that have good estimated breeding values for feed efficiency. And when we do that, we end up, and we take those bulls, and we mate them to a bunch of cows, and we end up with efficient progeny. We can do that and use it in the feedlot, and we can save about $10 to $15 in feed relative to an inefficient sire. You'll notice, and I'm going to bring this back later, is that the accuracy of these estimated breeding values is pretty good, 55 to 65%. You might not know much about that, but just note that for now. The other way of looking at this is one around sustainability. If I create 6,500 efficient feeder cattle and take them through the feedlot or take them through a year in a cow herd, I will save 475 tons of barley. That's that pile there. I measured it. It not only will save 475 tons of barley, but there will be a decrease in land use. And there will be a decrease in the carbon footprint. In other words, we're trying to improve the sustainability of beef. However, it took us a long time to do that and a lot of money. It took us 5 or 6 years just to be able to get those estimated breeding values and to create that database. So then the other thing we can do is, of course, molecular breeding values. We can take that same database and then create those prediction equations and just take a blood sample from an animal and say, how did you do? How good are you? This particular overhead just shows some traits we have, our residual feed intake, which is our favorite feed efficiency trait, and then a couple meat quality traits. But you'll notice right off the bat, the accuracy of these particular molecular breeding values are not as good. So it sort of decreases the progress that we can make. But exciting things are happening right now in the area of livestock genomics, in the area of sequencing. The cost of sequencing has dropped dramatically. And so the next level that we are going through, the world is going through right now, is in the whole area of using all of the genetic material from very, very popular bulls or individuals within each breed. And I'm going to show you how that works right now. Now, this particularly case is where within the Canadian Cattle Genomics Project, animals, very influential animals across the world in many breeds. You'll see the breeds down the side, but it's not that important. There's 10 breeds or crossbreds that are used here. And they were fully sequenced, and they're sequenced at about $10,000 a piece. And what the very first thing you'll see is that there's about 12 to 16 million bits of genetic variability that are related to some characteristic of the animal. That's tremendous. Also in that particular case, there's about 1 to 2 million more bits of genetic variability called indels. These are insertions and deletions. You'll see a sort of a little graph on the side that shows you what an indel type variability is. And these are naturally occurring, by the way. We didn't put them there. They're naturally occurring. Now, the exciting thing is when you look across all these breeds of cattle, there are 30 million bits of variability. 80% of those bits of variability have never been defined. This gives us tremendous opportunity for improving the accuracy. I'm going to show you, just in my very last slide before concluding, how this occurs. Essentially what we do in the very first row there, we have a low-density genotype. In other words, a 50,000 SNP genotype that we have on an animal for around $80. We can have lower density genotypes for less money. And essentially, you'll see right at the top there is that we have a pretty, not a very dense genotype on that chromosome, right? Every so often we end up with a genotype. The trick is, how can we fill in all those dots? How can we fill in the blanks? And that is through this process called imputation. It's a quantitative geneticist word. They love to make these words up. But essentially what it is we're extrapolating from the full sequence data to what this actually means. Let me show you. In the middle, we have our whole DNA sequence data. It costs us $10,000 an animal to get it. 300 animals, that's $3 million. This is tremendously valuable information. And let's go a little bit further. Just look at that segment that we're looking at. In these animals, these influential animals, we see that the most common sequence for that particular location is CGAGA. And so that's your answer, right? It'd be lovely if we had a course like that where we could actually put the answer. So essentially what we get is we get the actual sequence of a $40 to $80 test coming from $3 million worth of information and even more. And this will have tremendous improvements on improving the accuracy of our breeding values. Okay, in conclusion, here are some cows. No, in conclusion, the beef industry will continue to get better at sustainability. It will continue to use technology in all sorts of areas. Genomic technology will be one of those major technologies that has the potential to double the rate of genetic progress, particularly for difficult traits like feed efficiency, carcass and meat quality characteristics, and a low methane phenotype as an example, all towards getting a more sustainable beef animal, or what I call the climate-friendly beef cow. Thank you.